Well, hi everybody. Thanks for coming to listen to my talk, and also thanks for inviting me. Yeah, I'm based at the University of Glasgow, and today I'm just going to take you through some of the work that we've been doing to understand really the temporal dynamics of clearance and reinfection post-treatment when we're using both these egg and antigen-based diagnostics. And also, I know we have the chat, but if you'd like to get in touch later and ask any questions, you can find me on Twitter, or please feel free to send me an email. So just a brief overview of this quick talk, really. So I'll just lay out the question and why we think it's important. I think we all know, but it's always nice to lay it out. Give you an overview of some of the data that we're using to parameterize these models. I'll give you a brief description of actually the model framework that we've used so that you can hopefully have a better understanding of what we have exactly done. And then finally, the important bit, I'll show you some results. And before I start, I would just like to make some acknowledgements. So this work was done with Dr. Poppy Lamberton and Dr. Joaquin Prada from Glasgow and Surrey. And also a big thank you to all of our co-authors and obviously our funders. And so 240 million people are affected by schistosomiasis, which is prevalent mostly in tropical and subtropical regions. We can see this on this map here, where the dark orange indicates regions with high transmission, so across the African continent, in South America, so in like Brazil, and across China here. And it most commonly affects communities, obviously, without access to potable water and adequate sanitation. And control obviously largely focuses on mass drug administration with praziquantel to reduce disease, and also things like molluscicides, WASH programs, so increasing the access to water, sanitation and hygiene, and also health education. And though we know that a lot of these interventions have been really, really useful and really amazing, actually we're seeing that some locations still experience really high sustained transmission despite nearly 2 decades of mass drug administration. And for example, villages along the shores of Lake Victoria experience, again, really high schistosomiasis prevalence. And Mayugi, Uganda, just here, is where the Lamberton Lab has worked since 2004, working largely in these 3 schools, Bugoto, Bwanda, and Busubi, and getting really amazing detailed data, following the same students from year to year, and following mass drug administration that started actually in 2003. But as we can see here, so this is 4 years of prevalence estimates. You've got prevalence on the x-axis here. And I've just picked out a few years from this longitudinal data from 2004 to 2018. So we've got 2004, 5, 13, 18 here. And what we can really see is that this prevalence really has not changed over these years. And so the real question is why? And is this an operational failure or a biological failure? And basically, we hypothesized that regardless of the many reasons for operational failures, it would be characterized by rapid reinfection, whereas biological failures are more characterized by this insufficient clearance, despite these observed treatments that we're doing. And by biological failures, we mean things like schistosome evolution of resistance to the treatment, but also poor absorption of the medication by those being treated, or a high proportion of juveniles in those infections who are actually resistant to the treatment. And for some of the operational failures, we mean things like treating the wrong people, so missing out certain demographic groups, treating at the wrong time, so maybe not treating frequently enough, and also obviously insufficient treatment coverage, so actually we're just not treating enough people. And so to understand this persistent transmission, we need to understand the temporal dynamics of clearance and reinfection. And so for the purpose of this talk, I'm going to focus just on data from Bugoto. And I'm going to talk about an analysis that we've done from with data from 4 time points. So data were collected pre-treatment, 3 weeks, 9 weeks, and 6 months post-treatment. And 210 school-age children provided samples for CAT-CATs and CCA. And we actually scored the CCA tests in 2 different ways. So first of all, with the manufacturer's guidelines, which from now on I'm going to call CCA+. As a lot of people are probably aware, this runs from negative to triple positive. I got this figure from, or this picture from this paper, so thank you. And then we also scored them with the G score, which has been recently developed. And you can read more about that in this paper here. It was not developed by us. You can read about it here. But it was scored, it's basically is a scoring system from G1, which is negative, to G10, which is the highest positive score you can receive. This is a set of dummy cassettes that you compare your test to. And so that reduces, hopefully, the inter-reader variation, as well as increasing the resolution across all of these scores. So we've got 2 scoring methods here and CAT-CATs for each child. And these data were fit to a hidden Markov model. And the way that the hidden Markov model basically works is that we have this unobservable hidden state, which in this instance would be the infection status of each individual. So obviously we can't see somebody's true infection status, so that's our hidden variable here. And so you've got your infection status, you've got an observable process that generates your data, or gives rise to the observations. And because we fit this with a Bayesian framework, we have our data likelihood. And basically an individual can stay infected, or they can stay not infected, or they can switch between these classes, so obviously indicating clearance or reinfection. And it's these probabilities that we're interested in. And so to account for the CCA data, the framework is similar, but we just adjust the model slightly. And just as a brief description, we link the intensity of infection and the CCA test scores through a logistic function in this likelihood function, where the mean true CAT-CATs count, which is estimated by the model, is the real number of the logistic function. And basically what this just means is that the CAT-CAT score increases, and we make the assumption that as that CAT-CAT score increases, the CCA score will also increase. And that means that we don't actually have to make any assumptions about the interpretation of the CCA score, so the trace score, or the G2 and G3, which is the equivalent or believed to be the equivalent in the G-score system. Okay, so if we first look at prevalence pre-treatment, estimated by each of the 3 models, so there are 3 models here. One is parameterized with just CAT-CATs, one is parameterized with CAT-CATs and CCA+, and one is parameterized with CAT-CATs and G-score. And sorry, these peaks here are supposed to be filled with color, so you might not be able to see those so well, sorry. But this one here, this is your CAT-CATs. So this is the prevalence if you estimate this using just the CAT-CATs data here in green. And we can see that that's about 82%. But if we include the antigen data in here, the antigen test data here, we can see that both the CCA+ and the G-score data provide a higher estimate of prevalence, but they also perform comparably. And if we have a look at clearance and reinfection, so in this figure here, you have your estimates just from the CAT-CATs data. And your clearance is on the top, your reinfection is on the bottom, and down the side here, we've got total on the top row of both panels, and then you've got your time points. So you've got baseline to 3 weeks, 3 weeks to 9 weeks, and 9 weeks to 6 months. So these are the times between each of our time steps. And if we look at clearance, we can see that here, using just the CAT-CATs data, CAT-CATs would look like treatment was very successful. 93% of children over the 6-month period are clearing their infections, and only 35% of those children become reinfected within 6 months. But if we actually use the CCA+ data in here, we can actually see that 20% fewer children are estimated to clear their infection, suggesting treatment is actually less efficacious than the CAT-CATs egg counts would suggest. We can actually see here, so we've got 72% are clearing their infections in total, and 51% of those children are becoming reinfected. So you've got fewer children clearing and more children becoming reinfected within that 6-month period. And actually, if we use the G-score data as well, the estimates are quite similar. You've got only 65% of children who are clearing their infections, and 44% of those are becoming reinfected. So both the CCA scoring methods are estimating a lower clearance and a higher reinfection than we would estimate than we would obtain from just the CAT-CATs data alone. But one thing to note across all of these models is that most clearance does happen within 3 weeks of treatment. So this line here is 3 weeks, and of the total amount of clearance, we can see that most of this is happening within 3 weeks. And that most reinfection is actually detected by 9 weeks post-treatment. So of all the reinfection that's going to happen, most of it has already happened by 9 weeks post-treatment. So what does this look like as far as prevalence at each time point? So we can sample from the posterior distributions for infection prevalence over time. And this takes into account all of this clearance, all of this reinfection, and we can estimate prevalence at each time point. And you can see that your CAS-CATS is still in green. So we can see that this drop in prevalence at the 3-week mark, I think it puts it at around between 10 and 12%. But we can see that if we use the CCA plus and the G-score method for scoring the CCA tests, then we can see that actually prevalence, again, is around 20% higher and is consistently higher. And we get a very rapid bounce back in prevalence, so that by 6 months, we're really very close to the prevalence that we started at to begin with. And so to conclude, both the biological and operational failures are maintaining transmission, and this is indicated by this incomplete clearance and rapid reinfection. And obviously what this basically means is that the force of infection is not being reduced by this treatment. You can ignore the one in the middle, that was a mistake, that's not supposed to be there. And the next point to take home is that your frequent surveillance is essential. So 3 weeks post-treatment does capture the clearance dynamics, but it's too early for estimating reinfection, whilst 9 weeks post-treatment does capture the reinfection. And this really has implications for surveillance and monitoring programs.